Hello, welcome back to the course. We're looking at integrals of solutions, meaning we're looking at some first-order differential equations that are solvable by just integrating. And so this is section 1.1 in the book, which is at this URL. You can find the book. It's free online, or you can get a relatively cheap paperback, and that's probably the best way to support this project. All right. So let's just jump in. So we have a general first order ODE. Looks something like this, right? Or we can write it as this. And there's no, that's sort of too general to have to really have sort of like a crank solution, right? Where you just pop in the ODE, pop in the F really, and out pops an answer. It's just that doesn't happen, right? It's nothing. Nothing is so simple. For a certain specific, ODEs, we do have sort of a procedure, and depending on how bad the ODE is, sometimes we have a very nice procedure, sometimes it's a bit icky, but right, but that's life, c'est la vie, right? All right, so the first type, the simplest type, and it's really just the calc 1 at this point, is this sort of differential equation. So suppose that f, this right-hand side in this first order ODE, doesn't actually depend on y. Suppose it's just a function of x, right? So there is no y on the right-hand side here, right? That's the that's what we mean by we're looking at an equation like this. Now, in this case, we could just integrate, anti-differentiate both sides of this equation, right? If we anti-differentiate y prime, well, that's just going to be y, right? And if we anti-differentiate f, well, it's whatever the antiderivative of f is, right? It's really, this is what we're doing, right? And, don't forget to add the plus c, right? You've probably been drilled by now that you have to include plus c, right? Otherwise you lose points, right? But it's also, we wouldn't be able to solve the difference equation if we didn't put the plus c in there, right? Okay, so as I said, the integral of y prime, y is a function. Its derivative, if I anti-differentiate the derivative, I get the function back, right? That's what it means, right? So so y is just an antiderivative of f plus an arbitrary constant, right? So far so good. It's basically just calculus 1, right? Well, as you've seen in calculus, it can be tricky to find this in a nice way, but yeah, it's at least it's we have a formula for it, right? Okay, so that's the general solution, right? If you include the plus c, there's the general solution to this equation. If you so that includes all the solutions, and if you have an initial condition, then you can solve for the initial condition. You can get the c, and you can get the particular solution that you're interested in, right? So let's do let's do an example of this. Let's find the general solution of y prime is 3x squared, right? Presumably you can just guess this, but let's just do it. Write it out in more detail. So we integrate both sides, right? So the antiderivative of 3x squared, right? Well, it's the power rule. So if you undo the power rule, right, you get x cubed, right? That's precisely the derivative of x cubed. And I add the plus c, right? Now, we can always check things, right? And you should always, if you can, if you have time, when you're working out a problem, maybe you're taking a class, then you're going to be taking, an exam. You can always check these things, right? How do you check? You differentiate, right? So if I differentiate again, I mean, in this case, it's a little bit, a little bit overly simple, but yeah, you can differentiate, and if I differentiate, yeah, I get 3x squared, right? The constant vanishes, right? I mean, when I differentiate it goes away, and x cubed, well, I get 3x squared, right? So I precisely satisfy the equation, right? And this is the general solution to this equation, right? So now if I had an initial condition, I could find whichever particular solution I was looking for. All right, so this might be a good place to talk about this this notation over here. And what do we mean by that? It's the, by the indefinite integral, we mean antiderivative. So there's really no indefinite integral. There's only the definite integral. That's the only integral that there is. We just call the antiderivative integral because, well, you can compute it via a definite integral, right? We have this this formula over here. So an antiderivative, one of the formulas for an antiderivative that always works by the fundamental term of calculus is to write it as this definite integral. And that's really the reason why we use this, this notation over there for antiderivative, which is, in this case, what we're interested in. We're trying to find antiderivative of whatever f is, right? And so here is a formula. This is perfectly good formula. There's nothing wrong with it. It's you can always have your software, whatever software you're using, for like if you're actually doing computations, it's gonna have some some procedure to compute these guys numerically. You can plug in some particular x, and it's gonna spit out an answer, right? And it's just gonna it's gonna be really quick. There's it doesn't really have to do anything complicated. So this is integrating a function numerically that's a very well understood problem, and computers can do this very quickly. This is a great formula for y. There's nothing wrong with this formula, right? Now maybe one minor thing over here is x naught. That's just some initial value that you're integrating from. It's actually best if you use whatever your initial condition is, but it really doesn't matter where you start, as long as as long as you can actually do the integral. So if you are trying to do the general solution, right, start the integral somewhere. You have to make sure that the integral from x naught to x makes sense, so that you don't have that f doesn't like you're dividing by 0 somewhere on the interval or something like that. And then you add a plus c, and this is a perfect general solution to the problem, right? Now, it works even if there is no closed form formula. And you don't want to think of, just because there is no closed form formula for the antiderivative, you don't want to think, well, then this differential equation doesn't have a solution. No, it does. This is a perfectly fine formula for this for the solution for this differential equation, right? Now, usually you also have an initial condition, some x naught, some constant x naught, and some constant y naught, right? So that y at x naught is supposed to be y naught, right? So the best thing to do is to, well, that's the easiest place to start. That's the obvious place to start integrating from, right? Because it doesn't really matter where you start integrating, as long as the integral makes sense. And if you start integrating there, there's a simple way to figure out what c is. You can just let y naught be equal to c, or c be equal to y naught. So if I have this general form of these sort of differential equations, well, this is what the solution is, right? That's the particular solution to this equation with this initial condition, right? Now, why does it work? Well, is it a solution? Yes, by the fundamental term of calculus, it's a perfectly good solution, right? And I mean, when you differentiate, right, fundamental term of calculus tells you precisely that the derivative of this guy in terms of x is f. And this is a constant, so again, it goes away when you differentiate. Does it satisfy the initial condition? Well, just plug in, right? So plug in the x naught into the x, right? I mean, we're trying to get the y of x naught, right? So that's what we're trying to do. So we're going to plug in x naught into this formula. And, well, then it's just the integral from x naught to x naught. That's just 0, right? It's always 0, no matter what you're integrating, right? It's always going to, you're not really integrating anything. So, and then you're at y naught, right? So yeah, so it's exactly y naught, because this guy goes away. That's 0, right? So yeah, that checks out. It's that is the solution, right? So let's give an example. Like, suppose that I have this differential equation and this IC, this initial condition, right? At 0, it's supposed to be 1, right? And I can just write down what the formula is, right? It's that's what it is, right? You know, that gives me my solution, and that's really the best way that you can write this. There's no simpler way to write this, because there's no closed form solution for this. I mean, if you plug this into like Wolfram Alpha, it might actually give you what seems like a closed form solution, but it's actually just faking it. Well, you know, faking it. I mean, you know, it's basically giving a name to these sort of integrals and then pretending like they're closed form. So, right. I mean, that's, you know, does that mean closed form? I don't know. But there's nothing wrong with this. So, I mean, this is just what it is, right? And if you have software that, I mean, this is actually this type of integral. This is a very well-known guy, right? I mean, you're integrating the bell curve. So this is something that appears all the time in statistics. So, yeah, I mean, it makes sense to actually give this a name. So, you know, so normally, you know, this can be written in terms of, you know, something that's essentially just, you know, defining this integral to have a name, right? But there's nothing wrong with this, right? And if you have something even more complicated where you cannot solve it in terms of, you know, elementary functions, yeah, just write it as an integral. There's nothing wrong with that, because this you can just evaluate very easily. All right. So far, we're just doing Calc 1. We're not doing anything new. But so let's do something new. So suppose that I change it a little bit. Instead of having y prime as f of x, what if I have y prime as f of y? So now, instead of there being no x on the right-hand side, I have, there being no y on the other right-hand side, I have no x on the right-hand side, right? So the right-hand side does not depend on x. It's just a function of y. Now that I can't quite integrate immediately, but I can do a little trick, right? So first, write it in Leibniz notation, like this, right? You don't have to write it in Leibniz notation, but that sort of tells you what to do. So it's good to write it in Leibniz notation, right? dy dx is equal to f of y, right? Now, the inverse function theorem tells you, and this is where it's nice to write it in terms of Leibniz notation, because it sort of tells you what the inverse function theorem would tell you, and it's precisely that if I have, well, now if I do dx dy, right? So if I flip, right, I look at x as a function of y, well, I just flip the right-hand side too, right? So I have 1 over f of y, right? So now it's really, you know, that x prime, thinking of it as a function of y, so x prime of y, right, is 1 over f of y, right? You know, it doesn't really matter what we named the variables, right? So, you know, you don't want to think of, you know, the variables having some sort of, you know, implicit meaning, right? it's just two variables, right? So now we say, well, let's treat y as our independent variable, and let's treat x as our dependent variable, which is exactly the opposite of where we started, right? Over here, it was, y was the dependent variable and x was the independent variable. But okay, so this is what the inverse function term tells you. And now we can integrate, right? So, we write down, this thing, right? And say, well, we're just gonna, try to find some antiderivative, maybe in terms of a definite integral, maybe not. However, you figure out this antiderivative, and that's x of y. All right, what's wrong? Right. We have x in terms of y. That's not what we were looking for. We were trying to solve this guy, right? So we want y in terms of x. We want to be able to plug in x and get me y. And now I have to plug in what the value of the function is, and that will give me where I get that value, right? I mean, it's not quite the thing that I'm looking for, right? So I'm getting x in terms of y, but I want y in terms of x. Okay, well, let's solve for y, right? I mean, that's easier said than done, actually. If this antiderivative is not quite a nice some nice expression, it's gonna be hard. So but that's life. So all right, let's use this technique to solve an example, and we've done this guy before, but let's just we've guessed what the what the solution was, right? This was one of the four fundamental equations that we talked about before, right? And so it's just the exponential growth model, right? So y prime is k times y, where k is some constant, right? So how right-hand side, the k times y, well, that's just some function of y, right? It doesn't have any x in it, right? Now, I want to divide by it, right? So I want to do 1 over ky. So that wouldn't work if y was 0. So one of the things to think about as well, so what about y equals 0, right? What if y was 0? At least, what if y was 0 somewhere? And actually, it turns out y equals 0 is a nice solution, right? I mean, if I plug that into the equation, that solves it, right? If y is 0, its derivative is 0, right? So the left-hand side is 0, and k times 0 is 0. Yeah, so the right-hand side is 0 as well, right? So that works, right? So y equals 0 is the solution. So we have that out of the way, so we can assume, okay, so let's suppose that y is not 0. It's what happens in that case, right? That's the more interesting case. So in that case, well, now we can do this, 1 over bit, right? Now that makes sense, right? We're never going to be dividing by 0. So I write down, well, dx dy is 1 over ky, and now I can integrate, right? And if I integrate, so find the antiderivative in terms of y, right? So y is the independent variable now, right? And I get that x of y, right? X as a function of y is it's 1 over k times 1 over y, right? So 1 over y, the antiderivative is logarithm of absolute value of y, and then I add some constant. And that's, because this is not going to be our final constant, let me call it d for, but that's just some constant, right? That's the plus c, right? So there's just some arbitrary constant over here, right? All right, so now we have x. X is equal to this guy, right? So now we want to solve for y, right? Well, that's not too hard, because I can just exponentiate, right? If I exponentiate, you probably first move the d over to the other side, multiply by k, then exponentiate, right? Sorry. So you get, that's just simple. pre-calculus kind of stuff, right? So I solve for the absolute value of y, and it's equal to this thing, right? I could pull out the e to the minus kd out in front, so I have almost the thing that we said was the solution to the exponential growth model, right? I mean, there's a couple of things, right? I have the absolute values over here, and then I have this instead of a arbitrary constant. Now, if d is arbitrary, e to the minus k d is also kind of arbitrary, but the exponential is always positive. So that's actually always a positive number. But we also have these absolute values. I'm sort of highlighting, over-highlighting. You wouldn't be able to see what I'm actually highlighting. These absolute values, right? So yeah, I mean, I should get something positive on here, right? But if we think of an arbitrary c, so including negative, right, and we would write y is c e to the kx, right, then we get we get both signs. We get both where y was positive and where y was negative. And we actually get even y equals 0, right? So we separated that out here, right? But if we write the solution like this, then, if we think of c as arbitrary, that it includes when y was positive, right? In which case there were no absolute values, right, over here, and there was a positive constant down here. When y was negative, well, you could remove the absolute values, but put a negative sign here. That meant that the constant was negative. And when 0, well, just, if c is 0, then y is 0, right? So actually, this expression includes all the solutions, right? And yeah, we know that that's what it does, right? I mean, that's what we said when we were discussing it before, right? That's the general solution to this equation, right? But now we got it by integration. All right, so let's look at another one. Let's make it slightly more complicated. Instead of one, and let's not have any k in there. Let's just put y squared in there, right? So instead of ky, I'm going to have y squared, right? And let's put some initial condition here. So y at 0 is supposed to be 1. Okay, so again, I want to divide by y squared. So if y was 0, that wouldn't be possible. But y at 0 is a nice solution, right? So we don't really worry about y at 0, y being 0, because that is a solution, right? Again, the derivative of 0 is 0, right? So the left-hand side is 0, and the right-hand side, well, is 0 squared is 0. So that's also 0. So yeah, so it is a solution. So let's just assume that y is not 0, and let's divide. So apply the inverse function theorem, right? We integrate. Now it's easier than with the logarithm, right? It's just minus 1 over y is our solution, right? Well, now it's it's still in terms of still just x in terms of y. So we want to solve for y. Yeah, that's what it is, right? 1 over c minus x. Yeah, easy, right? So we either have y as 0 or 1 over c minus x, right? That's our general solution is this thing, right? So we can't really easily write it in as one expression, but who cares? 2 expressions is just fine, right? So that's our general solution. We still have an initial condition to get a particular solution, the particular solution we're interested in. So let's plug that in. If you plug that in, right, x equals 0, you get 1 over c on this side, and that's supposed to be 1. So 1 is 1 over c. So c is 1, right? So you let c be 1. So this is our solution, right? 1 over 1 minus x. Now you notice this solution has a singularity, right? It blows up when x is 1, right? I mean, I cannot plug in x equals 1 because I'd be dividing by 0. If I look at the graph, right? I'm really starting over here, right? When x is 0, y is 1, right? And then, then I'm following this, maybe backwards and forwards, right? And it blows up. It goes to plus infinity, right? Now, this expression is also defined over here, but it's not really our solution, because our solution really starts over here, so we're only following it, following this line. So really, that's just our solution. Now, think about, y squared is so nicely behaved, right? I mean, how, it's a nice polynomial. It doesn't have any x in there. It's y squared, right? I mean, there doesn't seem to be anything wrong with it, right? And it's, we definitely, you don't really see from this, it's not immediate to see why should this, the solution blow up, right? Why should the solution have a singularity? Why should the solution just not exist further on, right? But it doesn't, right? So, well, that's what it is, right? So now, as I said, y is really only defined on minus infinity to 1, right? Because that's where our initial condition is, right? Because it's this thing is not really connected to this, right? So this is just, it just happens to be come from the same formula, but really you only want to think of the solution to this equation on this interval, because it blows up at 1. There's no, like you're not going to get through that, right? Even though you have some sort of a formula, but it no longer makes sense for this equation, right? So, right, because 1 to infinity does not include our initial condition, because the initial condition was at 0, right? So, all right. So yeah, it's it might seem really nice. It's a really simple one, but yeah, we could get these sort of singularities. Yeah, c'est la vie, right? It's still not too bad. I mean, it was actually solving it was very easy, right? But yeah, we do get we can get these singularities. Right. Oh yeah, I said that already. Right. It's the right-hand side of the graph is not part of our solution, right? All right. Now, let's go back to the beginning. So let's forget about the right-hand side being a function of the dependent variable. Let's just suppose it's the independent variable. Now, typical word problems that you would solve that way, and that you did solve in Calc 1, were things that deal with velocity, acceleration, distance, those sort of things, right? So, for example, if I have a car and it drives at e to the t over 2 meters per second, where t is the time in seconds, right? I could, ask some question about it. How far did the car make it in 2 seconds, right? So, if it starts at t equals 0, where is it at t equals 2, right? How far it is, right? And you know the speed, right? How far is it in 10 seconds? And it's basically a Calc 1 problem. Well, you have to give names to things, right? So we already have t, as time, but we have to give a name to the distance. Let's call it x. Why not, right? We just call it x. So let x be the distance traveled, and so the equation is, well, if x is the distance traveled, x prime is the velocity. So velocity is e to the t over 2, right? And so the general solution here is this thing, right? I mean, I just integrate, and integrating e to the t over 2 is very easy, right? So that's the general solution, right? That's just Calc 1. And at t equals 0, x is supposed to be 0, right? I'm supposed to start, it's the distance traveled from t equals 0, right? So I'm going to set my initial condition to be 0 at 0, right? So x of 0 is 0, right? Now, if I plug that in, right? So I get, well, so 0 is 2 plus c, So c is minus 2, right? So my solution is 2 e to the t over 2 minus 2. That's our solution, right? That's the solution that satisfies the initial condition, right? So so what are we interested in? Where are we in 2 seconds? Where are we in 10 seconds, right? So at 2 seconds, well, that's just x of 2, right? Well, x of 2, I just plug in. So that's approximately 3.44. And everything was in meters. So that's how far we made it. And at 10 seconds, we're actually quite a bit further. We're at 294 meters, right? So, all right. So that's sort of a typical example of just a differential equation word problem where it's the independent variable on the right hand side, right? Now, another type that you've seen before. So suppose that we have acceleration. So let's suppose that the acceleration is d squared, right? So we're accelerating, and not just accelerating, we're accelerating more and more, right? So d squared meters per second squared, right? That's what acceleration is. The units of acceleration are. So at time t equals 0, let's suppose that the car is at the 1 meter mark and it's traveling at 10 meters per second. At time t equals 0, right? Let me put this here. So question, where is the car at time t equals 10? If you think about it, this is a second order problem. This is not really a first order ODE. This is a second order ODE. So again, let x be the distance, right? Distance traveled. Well, then x prime is the velocity, but acceleration is actually x double prime. So we didn't really think about how to solve if we have a second order. But in this case, it's not too bad. So the full problem is this, right? We have x double prime is t squared, x at 0 is 1, and x prime at 0, so we actually have another initial condition here. X prime at 0 is 10, right? That's really the full second order problem that we're trying to solve, right? It's not too bad. So we're actually, it's really two first order problems. Now to make it first order problem, just give x prime a name, right? Call it v, velocity, right? V is x prime. I'm basically adding another variable, another equation, but then I just solve a different problem. I solve this problem, this first order problem for v, right? I know that v at time t equals 0 is 10, and v prime, which is acceleration, is t squared, right? So I can solve that for v. And once I have v, I plug that in, right, to this equation, really, right? Because I know that x prime, which is that's the velocity. Well, it's supposed to be the velocity. I know what the velocity now is, right? So I have this equation, and now I use this initial condition, right? Okay, so we'll just leave that as an exercise, right? So basically, you solve two problems. You first solve this problem, and then you solve this problem, right? Once you know v, you plug that into here, right? You solve that problem, and then you plug in 10 for t and get what x is, right? Okay, but I mean, you've seen these sort of things in calculus already. So, all right. So that's it for today. So see you next time.